would like to present our program DC-Integra, which is one program in the group DC Foundation for foundation engineering analysis. And here we have a large number of different programs for different types of walls, foundation bed walls, cantilever walls, reinforced earth, footings, piles, slopes, groundwater lowering, and so on. DC-Integra means integrated foundation engineering, and it supports an overview over the complete project based on a plan. And it allows you to define different analysis sections and to jump automatically from DC-Integra into the corresponding analysis program and transfer all the data from our 3D model of the complete foundation pit. DC-Integra has different parts for the customers that can be purchased differently. So we have a basic program 2D, it's just a 2D plan for displaying the kind of walls and so on. We have DC-Integra 3D as the 3D model of the complete foundation pit, and the slopes if we have different depths in the base of the foundation pit. Then we have the option DC-Integra volume, 3D volume for the automatic calculation of the excavation volume. We have DC-Integra 3D pipeworks for the display of different types of pipeworks in the 3D model. And finally, DC-Integra 3D anchor for the check of anchor collisions between anchors and pipeworks, or between anchors and buildings. If we start a new plan, we have the possibility to import a DXF file to have the basis for the plan as a background, or to draw directly our foundation pit here in a special scale to be freely defined. And here we have our XY system with coordinates running here to define our system. First, we may import ground level points. So from an easy text file, import ground points. We can select the file. And first we have a short overview. What is the content of this file? The first 3 lines show that we might hear some point name, and then coordinates X, Y, and Z. And we can define for the program which column to use for which kind of data. So X is the second column, Y the third one, Z the fourth one, and the name of the point is the first column here. Then we might move or shift these points, and we have a filter function. So if you have a very large number of points, if you have several thousands of ground points which don't have big differences in their height, we can filter these points to have, for example, not more than 1,000 points, and the program not being too slow for a large number of points. So in this case, we have some points displayed here. And we could work with levels above sea level. In this case, we just have local heights, so I switch this off. And I don't want to change the point that I just imported. And now we have a small example of a ground surface level, and we see this in the 3D display. If we rotate here and enlarge the view, we see that there are some differences in the height, not big differences, but this is the level of the ground surface, which is also used for the excavation volume. Now if we go back to the 2D, for the soil layers, we need the same order of the layers all over the area that we are covering here. You have the possibility to interpolate at any point which soil layer levels we have, because the depth of the soil layers may be different at any point. So for example, we first create the order of the soil layers. We have, for example, some silt with thickness of 80 centimeters. We can enter the data directly here, or we can use some parameter suggestions. So if the same kinds of soil layers are appearing again and again, we can just use here this suggestion, and we have the parameters predefined here. The second soil layer should be some sand with an angle of internal friction of 35 degrees, for example, to a depth of 2 meters. Then the third layer being some gravel to 5-meter depth. And finally, the last soil layer should be some clay with a lower angle of internal friction and a little cohesion to a depth of 10 meters. So we don't use these depths at the bore points because these are only ground surface points. But we can then use these soil layers at different bore points where we really have information about the soil layer depths. These are normally less points than for the ground surface. So we can define a bore point at this position here, for example. You see we have the soil layers here predefined. And I can't change the names or the parameters, but I can change the depth of the soil layer. So here we have only 40 centimeters for the first soil layer, 1 meter and 10 for the second, 6 meter and 50 for the third. And instead of creating a new bore point, we may as well double click on ground surface point and add the soil layer here to this point. So for this point, we have the ground surface and we have the soil layer depths. So here we have a larger depth for silt, 2 meter and 80 for sand, and for example, 3 meter and 20 for gravel. And I just add 2 more bore points down here. A little more silt, only a little layer of sand, and a larger level of gravel. And the fourth point should be here with the depths that I predefined. So we have one area where the soil layers are defined, and we can interpolate at any point which soil layer depths we have for the analysis. Now we can define our foundation pit area, and here at the bottom we have the 3D functions. This is for the base of the foundation pit. So this foundation pit may have an arbitrary shape, like a polygon. And first it should have a constant depth of 5 meters. And now we can define that certain lines are special kinds of walls. So I would like to select all the lines. So I use this complete area, and I deselect the area inside. So in red we have just the surrounding lines. And with the right mouse button, I can change the properties of the lines. So this should be a sheet pile wall, for example. Now for sheet pile walls, we have a large number of types predefined, like Arbet, Larsen, Hirsch, and so on. This is a large list of profiles which can be changed and can be added. And for example, we use a Larsen 607. And if we confirm this, you see that we have now the wall with the real measures of the soil, of the sheet pile profiles. And we see one first problem here. If we have, for example, sheet piles with a length of 60 centimeters, and the length of some line of our foundation pit is not a multiple of this 60 centimeters, we have these corners with gaps, and we see this in the 3D display. There are gaps that we don't want to have here. And on the other side, we have the walls at the level of 0, which doesn't match to the ground surface. So we want to change this. First, for these gaps between the sheet pile profiles, we have a special function. If I double click this line, we can use the function adjust length. And then all the lines are changed to a length which is matching to the sheet pile profile width. So these corners here are closed now. And we have a second function for adaptation to the ground surface level. Here on the project, adapt heights. And we can adapt the ground surface to the wall or the wall to the ground surface. Here I want to adapt the wall with a certain overhang above the ground level. And then the sheet piles are changed. And we can see this in the 3D model. At first, we don't have any gaps here in the corners. And we have the wall at the right level above the ground surface. So we have a closed foundation pit at this position now. Now we can change the lines to different types. For example, we might here don't use a sheet piling, but use a slope with an angle of 45 degrees, for example. And now if this line is the bottom of the soil, of the slope, the program automatically intersects with the ground surface. So we see now we don't have a horizontal ground surface, we have different heights of the ground. So the intersection between the slope and the ground surface is not a straight line. And this is what we see again in the 3D display. If we have different heights here, we have a different position where the slope is intersecting with the ground surface. And this is calculated automatically by the program. Now we can have different types of walls. For example, here at the right, we would like to have a bore pile wall with 64 centimeters diameter of the piles. We have a negative spacing, which means there is some intersection. We have an intersected bore pile walls with an arrangement of 1, 3, 1, which means that we have 1 reinforced pile and 3 non-reinforced pile. And here this side would like to have a girder plank wall with girders HEB 300 and a distance of 2 meters, for example, infilling from timber. And then we see in the 3D display that we have all the different materials here. We have reinforced concrete for the bore piles, we have steel for the girders, and we have timber for the infillings. So this is the 3D display of the different materials that we have. And then we can have different depths of the soil, of the foundation pit area, which means that we can use slopes here in between. For example, there should be a slope here. Okay, it should be in this position. And for example, the blue section should be only 4 meters and 50 deep. And in between we have a slope with 45 degrees. And this line is the lower edge of the slope. So we have the slope here between these two areas. And this is, again, this is also interpolated here in the slope at the outside. We can define a second slope here. The blue section being 5 meters and 80, for example. Lower edge. This doesn't work here at this position. Let's have some slope on this side. Here 6 meters and 10. Then there could be some slope in front of the wall. Here being only 5 meters and 20. And you see that we have a different intersection between these slopes in the base of the foundation pit. And we see this again in a 3D model, that all these slopes and intersections of slopes are calculated automatically in the 3D model and displayed here in the foundation pit. Now before we had defined the soil layers, and we can display this as well in the 3D model with this view function. We can activate the soil layers, and first we see where the foundation pit goes into which soil layers. We have a smaller thickness of the first soil layers here. We have a larger thickness here. And all these different soil layer levels are interpolated at different points of this region. Okay, we see that this foundation pit walls here go into the gravel, and here we just go deeper into the clay, which is the last soil layer. And for example, we can switch off the transparency and the bounding areas. And in this case, we have a better overview where is which soil layer and where does it meet the foundation pit walls here. So there are different options what to see and what to show in this 3D model. If we select to display only the part outside of the foundation pit, we have the foundation pit shown here and have the soil layer model outside. And one function which is quite nice, if I switch off the ground surface and the foundation pit, and then the area only inside of the foundation pit, then we have the soil block. We have the bounding areas as well. We have the soil block, which has to be excavated. This is just the excavation block which is needed to create the foundation pit. You see that we touch a little bit the clay here. In most of the area, we just go into the gravel, which is shown in yellow. And now this excavation volume can be calculated automatically. If I go back to the 2D, we have the function of the volume. And here we see separated by the different soil layers, which volume do we have with a certain swell factor, which might be more than 1, which increases the volume during excavation. We can have the cubage to be transported. And with a specific weight, we calculate the excavation mass in tons. And so we have about 4,600 tons of soil to be excavated to create this foundation pit. Now, for these walls, we also may define anchor layers. So, for example, along this wall, you see the height of the wall. We can define a new anchor layer at 1 meter and 20 depth, for example. And the first anchor could be at 70 centimeters from the start of the wall. And the last anchor should be not nearer than 50 centimeters to the end of the wall. We have an anchor distance of 2 meters, anchor length 10 meters, an inclination of 15 degrees. The fixed length is 5 meters with the diameter of the press sector, the projection in front of the wall, and we can have horizontal angles or anchor spreading. If you have 2 anchors with a certain angle in between, you can define this here. So with a second anchor layer with the same parameters, then these anchors are shown here, and they're shown as well in the 3D model. If I switch off the soil layers and switch on the foundation pit and the ground surface, then we see that here we have the different anchors at these levels. We see as well the boom inside of the foundation pit. If I defined it, here we can select the boom profile, for example, 2 times U180. If this is defined, then we can see it in the 3D model. So we have here the booms holding the anchors. Now, if we have this system complete, we can define analysis sections. And this means if I have an analysis section here, I want to calculate this sheet pile wall, section A, then DC-Integra automatically knows if this is a sheet pile wall, the corresponding program for analysis is DC-Pit. And we have to use this program for the calculation. So we can define a new project file and start the analysis programs. So DC-Pit automatically comes up and shows all the parameters which are already defined. You see we have our sheet pile wall here, which is a Larsen 607. We have a certain ground level height, which is a little lower than the head of the foundation pit wall. We have the soil layer levels interpolated at this position, at this analysis section. We have the excavation depth and we have the anchor levels. So we can perhaps add some excavation stages here and then make the calculation. And if this calculation is finished, we can automatically integrate result graphics into DC-Integra. So this means if we are in DC-Integra, we can select to insert some graphics from this analysis section, and it should be placed here at this position with a certain size. And then for DC-Pit, we can select which graphics to use, for example, the geometry graphics and the section forces from total loads. I switch off some other graphics. So we have two pictures, and these can have a certain scale with the size of graphics that I selected. And then we have the graphics here in our plan, which are coming from the analysis. So these were the parts DC-Integra 3D and 3D volume for the volume calculation. Now we can define different types of pipeworks. And these are first only simple lines. So for example, if I have a wastewater pipe here around the foundation pit, I can select both lines and then with right mouse button define the properties. So the wall type is in this case not a wall but some pipeworks. I would select some wastewater pipe. I can define some profile with diameter 500 millimeters, for example. And then for this line, which originally only has X and Y coordinates, I can define a depth of the bottom edge of this pipeworks, which should be, for example, in a depth of 7 meters and 50. Then all these pipeworks are displayed in the 3D model. So we see the pipe here with 50 centimeters of diameter. So this is the part of 3D pipeworks. And for a larger model, I have some predefined example, which contains a larger number of anchors and so on. You see here, we have different levels in the foundation pit. We have some pits here. We have several intersections of the slopes, which are created here in the 3D model. All these different intersections here. And now we can check for anchor collisions. That means if we have different anchors, for example, in this corner here, there might be some conflicts. And under settings configuration on the page display, we can define which distances must be kept to have no problem, for example, between two anchors, or which distance may I have to have between an anchor and a pipework, or between an anchor and the building. This can be defined here, and then we can check. And in this case, we have 42 collisions with these anchors that we defined. So where are these problems? We can see this in the 3D display again. So you see, if there is a problem with these anchors shown in red, the minimum distance is shown here. Where is the problem? We have only 1 meter and 3 as a distance between two fixed lengths. And the required distance, for example, should be 1 meter and 50. The same, we have, for example, here a distance too low from the anchors to the pipeworks. This is less than 1 meter. This is not enough. So we have to change the parameters here. So we go back to the input and select this anchor layer, edit this anchor layer here, and in the properties of the anchors, the inclination should be, for example, only 15 degrees. And if I check this again, we have only 27 collisions left, and we see that is not calculated again. We have 27 here. And I need to have the 3D model recalculated. Let me reopen this example. Okay, I think I was on the wrong side because the problem is solved at this side here. Here we have now enough distance, and this is a different anchor layer at a different wall, which was not changed. So we don't have a problem here again, but we have, for example, a problem between these anchors and the building. So if only single anchors have a problem, not all the anchors, we see this as well. If we edit the anchor layers here, then we see from these anchors, only 2 in this layer have a problem with some distance, and I can double click one single anchor and try to change some parameter to avoid this conflict here. So if we want to define a building, this is just a polygon that we can define. For example, there could be a building here. And then we can define a depth of this building. So the top edge is at a negative depth as a height. So for example, -5 meters and a depth of 3 meters and 50. And we can fill this with a certain color to see the different buildings here. So this is this polygon with that defined height or depth shows a building in our 3D model. In addition to these analysis sections, we can have geological sections like this one, which doesn't cut only through one wall, but through the complete model. And with this section, we can select here a geology section, which should be inserted into the current plan or could be created as a new plan. For example, with a maximum depth of 10 meters, we want to insert the graphics here with a certain scale. And we see the soil layers, we see the walls, we see the base of the foundation pit with all the slopes and pits. And this can be defined within this plan. So finally, for this complete 3D model, we have an IFC export for BIM programs. So under File, Export IFC, you see that we support reference view and design transfer view. Depends which program uses which kind of view. And if we export this example, we can, for example, open it in Solibri. It is this IFC file. And then if we optimize the zoom, you'll see that all the walls, the base, the booms, anchors, pipeworks, everything is integrated here in this IFC model. And if we select one wall, for example, this wall has quite a number of single sheet pile profiles. So we see any single profile being defined in this model. Or we have the fixed length of one anchor here, we have a pipework here, we have this boom, which is defined as a 2 times U 220, and so on. So we can integrate all this data into different programs to use it in a BIM model. So far as an overview over DC-Integra. So thank you for your attention, and if there are any questions, please feel free to contact us.